Thank you for the invitation. I am pleased to accept it and to introduce the next speaker. I not have to say too much because you said it this morning that we met in Oberwolfach long back and we met in many places very often. And so I am happy that I am the chairperson for your lecture. And you are going to speak on the second order duality between prime factors and prime number in arithmetic progressions. So please, Krishna.
First, my thanks to the organizers for the invitation to speak at this conference, and my thanks to Michelle Waldschmidt for introducing me and chairing this session. This is the correct talk in case you think I have the wrong slides. I gave this talk for 1 hour at the conference at Penn State University earlier this year in June, a conference in honor of the 85th birthdays of George Andrews and Bruce Butt. So what I'd like to say is the legacy of Ramanujan Conference, and now we are doing the legacy of Srinivas Kotyara and Kalyan Chakrabarti Conference for their 60th birthdays. The only difference is that instead of 1 hour, I have to give this talk in 30 minutes. So naturally, I won't be going through all the slides of this talk. So this is joint work with my PhD student Jason Johnson, who just on December 4th defended his thesis successfully. So he just completed his PhD. So this is sort of a rough outline of the talk. I will focus on 1 and 2, talk a little bit about the analytic approach, and then without going into too many details, I will discuss the main ideas relating to the uniform distribution of the second largest prime factor and how that gives the main results. Okay, so let us begin with the 2 classical results of Edmund Landau, who showed that the sum of the Mobius function up to x, which is denoted by m of x, is little o of x, and the series summation mu of n over n from 1 to infinity being 0, both of these are elementarily equivalent to the prime number theorem. That means if you assume these results, without too much difficulty, you can deduce the prime number theorem, and vice versa. If you assume the prime number theorem in its simplest form, pi of x asymptotic to x over log x, you can get both of these results. Okay, so this is famous 2 equivalent theorems of Edmund Landau. All right, now, of course, strong form of the prime number theorem with error terms yield corresponding bounds for m of x and corresponding bounds for the tail x n from x to infinity of summation mu of n over n. Okay, so they are very similar. All right. Now, this work actually goes back to my PhD thesis of 1977. Just to make one comment, after the Ramanujan centennial, the focus of my research shifted to the theory of partitions and Q series, hypergeometric series. So for 25 years, I was not working in analytic number theory. I came back because 2 or 3 PhD students came and said that they would like to do the PhD with me and want to work in analytic number theory. But also there's something else that happened. These results in my PhD thesis of 1977, which was, I wouldn't use the word ignored, but which was not so seriously looked at by the international mathematical community, suddenly got the focus from about 2017 onwards, primarily due to the efforts of Ken Ono, and now there are a whole bunch of papers relating to this, which they have termed as Alladi duality. So that was another motivation for me to go back and look at this work and see other problems that can be given to these PhD students. So I'll come to that very soon. So the very interesting duality that I noticed in 1977, actually when I was here in Madras for the summer, that's when I found this, was you take any function f defined on the primes. Little p of d is the smallest prime factor of d, capital P of d is the largest prime factor of d. So if I sum mu d, f of the smallest prime factor of d, over all divisors of n which are bigger than or equal to 2, I end up getting minus f of the largest prime factor of n, and vice versa. So I was quite excited noticing this because it is so simple and it is elegant, so I knew that it has to have some consequences. right? So I started investigating consequences of this. So here is one very interesting result. If f is a bounded function on the primes such that this function has an average over the largest prime factor, let's say the average is c, then the series from 2 to infinity, mu of n, f of the smallest prime factor of n divided by n, is minus c, and vice versa. So if the series converges, then that average exists, but it's c to minus c. Okay, so this is the result that you get as a consequence of that duality. Of course, quite a bit of analytic work is needed to get this, but this is the result that you get. Okay. Now, this is actually a surprising generalization of Landau's result. So take Landau's series, summation mu of n over n from 1 to infinity equal to 0. Remove the first term. So write it as summation mu of n from 2 to infinity is minus 1. Now go back to this equivalence. Choose your function f on the primes to be identically 1. Then obviously the average is 1. So c is 1. And that means the sum in 6, mu of n over n from 2 to infinity is minus 1. So that's Landau's result. So my result here is a very broad generalization of Landau's theorem. Okay, so I was quite excited when I got this. But we need some striking special cases. To make any theory interesting, you must have some really striking special cases. So special case the following. Choose your function f on the primes to be the characteristic function of primes in an arithmetic progression L mod k. So now the point is this. The prime number theorem for arithmetic progressions says that the sequence of primes is uniformly distributed in the reduced residue classes modulo k. So one of the things I proved was, if you assume the prime number theorem for arithmetic progressions, then from that you can show that the sequence of largest prime factors, that means it is the sequence of primes but with repetition, right? Like largest prime factor of 2 is 2, largest prime factor of 3 is 3, largest prime factor of 4 is 2. So it is really a sequence of primes but with repetition. That repetition does not destroy the uniform distribution property. It takes some effort to prove this. So I proved that the sequence of largest prime factors is uniformly distributed in the reduced residue classes modulo k, which means if f is chosen to be the characteristic function of the sequence of primes in the reduced residue class, this average c is 1 over phi of k, which means the series mu of n over n from 2 to infinity, but now with the condition smallest prime factor is L mod k, will be equal to minus 1 over phi of k. Now this is very surprising. Why? Because what is really happening is that series is convergent, conditionally convergent, and it goes to minus 1, and you are slicing that convergent series into phi of k sub-series, but you are slicing it in such a way that all the sub-series have the same value, minus 1 over phi of k. I don't know of any other example of slicing convergent series into equal valued sub-series. Divergent is easy. You take harmonic series that diverges, take the sub-series of all reciprocals of evens, reciprocals of odds, because in a divergent series like that, the contribution comes at the end. So it's the asymptotic distribution that is important. In a convergent series, it's very sensitive to the initial values. So you can't just slice it and say, I will now get 5 sub-series all equal to 1/5 of the original value. I have challenge. It's not easy. So this is the first example I found of slicing such a series. So I was quite excited by this. But what is interesting is, this is related to the prime number theorem for arithmetic progressions, just as Landau's result is related to the prime number theorem. So this was my PhD thesis. And what happened was, from 2017 onwards, this has received considerable attention and generalized in the setting of algebraic number theory by the use of the Shabatarov density theorem. I'll come to that later in the lecture, by a whole group of young mathematicians, but primarily with the impetus given by Ken Ono. So these references will come later. Okay. So now, in that same 1977 paper, I had higher order dualities. So here pk of n, capital Pk of n and little pk of n represent the largest and smallest prime factors of a number. Of course, these are defined only when the number has at least k prime factors. So you set f to be equal to 0 if omega n is less than k, the number of distinct prime factors k. But now the duality is, if I sum mu d, f of the kth largest prime factor of d, okay, I do not get the smallest, kth smallest, I get actually only the smallest, but with weight omega n minus 1 choose k minus 1 with a sign attached. And then this can be reversed. Okay, so this is the higher order duality. All right. And if you use Mobius inversion, you can rewrite those two identities in this particular form. Now, I never investigated consequences of this higher order duality after 1977, and nobody did, which doesn't mean it's uninteresting. It's just that people don't look at it. And sometimes when people don't look at something, it's an opportunity for you to do something interesting. So after Ken Ono and this group started looking at these algebraic analogs, another PhD student came along, Jason Johnson, and I said, you know what, we should look at these higher order dualities and let's look at k equal to 2 to begin with, and let's see what we end up getting. So that's the thrust of this talk. So when you have k equal to 0, k equal to 2, that's the identity that I'm looking at with the smallest prime factor. Now, just as you have summation mu of n over n from 1 to infinity is 0, you can show that summation mu of n omega n over n from 1 to infinity is 0, but this is more difficult to prove, okay? And I will tell you what is involved in the proof of this. But now if I peel off the first term corresponding to n equal to 1, like I did for the classical Landau result, I still end up getting, so the sum from 2 to infinity, mu n omega n over n is still 0. Previously I had a minus 1, but now it's still 0. Okay, so the main result now is, just as we proved there that the sequence of largest prime factors is uniformly distributed modulo k, we now prove that the sequence of second largest prime factors is uniformly distributed modulo k. But this proof is more difficult compared to the distribution of the largest prime factor. And I will tell you why it's more difficult. But once you have that and we use our duality, you can show, and this is our main result, that if I take that series mu n omega n over n from 2 to infinity, but now I impose the condition smallest prime factor is L mod k, I once again get 0 for every residue class L, which means I've taken that original series whose value is 0 and sliced it into phi of k equal valued subseries, and of course all equal values are equal to 0. Okay, so this comes out as a consequence. So this is our result, and recently we have posted this paper on the archive. So I'm going to give you some idea as to how we get this. Okay, so now I want to tell you a fundamental difference between the largest prime factor and the second largest prime factor. The fundamental difference is this really important counting function, psi of xy. This is there's a typo there, it's largest prime factor less than y. So this is the number of integers up to x whose largest prime factor is less than or equal to y. This is actually quite small when y gets small compared to x. So let's denote by alpha the ratio of logarithms of x and y, which means y is x to the power 1 over alpha. So as alpha increases, so square root of x, cube root of x, fourth root of x, and so on, the psi of xy becomes much smaller in comparison with x, and it's x times, this is an actual bound, e to the minus alpha over 2, but it's even much smaller than this. Whereas, if you look at the second largest prime factor and ask for the number of integers up to x for which the second largest prime factor is less than or equal to y, it is not that small. Why is it not that small? If you choose the second largest prime factor equal to 2, you can't make it smaller than that. Every number of the form 2 times the prime has second largest prime factor 2. And so the number of such integers is of the order of magnitude x over log x. Of course it's little o of x, but it's not that small in comparison with x. So naturally when y gets bigger, it's maybe still little o of x, but it's not going to be as small as psi of xy. So that makes all the computations much more difficult, because many of these convergent things have to be handled much more carefully because of the fundamental difference between the growth rate of psi of xy and psi 2xy. So I just mentioned this as a fact. Okay. All right. So next difference. the sine m of x, which is upper bound is given here. This comes from the strong form of the prime number theorem. It changes sign infinitely often. In the case of summation mu n omega n, that should be an n by the way, this sum m omega of x is asymptotic to constant x over log squared x, which means it will not change sign infinitely often. But it does change sign for another reason, but only finitely many times. Okay, so it's on the same side. All right. So there is a significant difference between the behavior, and that actually adds to the complication of this, of establishing these results in this particular case. All right, so I just want to say exactly how we do this very quickly. So what we do is we look at m omega of x, which is this sum that I have. I express this omega n as the sum over the count of the number of prime divisors of n, and I reverse the order of summation. So I get a summation mu of n over integers which are 0 mod p. You write n as m times p. Because of the Mobius function, your m and p must be relatively prime. So I rewritten this way, so it leads to the investigation of a sum which I call mp of x over p, and that is the sum of the Mobius function up to x, where these numbers n will not have a prime factor p, and one can obtain a uniform bound using the Perron integral method that's valid for all p up to x. Okay, so this comes out. All right. And once we get that, we have to go back and split this sum into two ranges, p less than or equal to t and p bigger than t, and work with this, choose t optimally. And when you do that, you end up getting a bound which is only of the size of x over log x. And this x over log x is because the primes come in, and without further investigation of the cancellation, you can't do any better. So you get a bound of x over log x, but that's still good enough. It's still little o of x. Now the next thing you do is a very familiar technique to all the analytic number theorists here. You take the same sum and put a fractional part of x over n as a weight. You go through the method of Axer, and then you end up getting little o of x, but there is a loss in terms of the quality of the upper bound. The final thing is you look at the integral part. Now you use the fact that if you sum mu d omega d, that is the negative of the characteristic function of the prime powers. So when you do that, this sum becomes minus x over log x, and you add everything up, you end up getting the fact that this sum becomes 0 because I have to divide by x, and that is how you first get the sum mu of n omega n over n, and from 1 to infinity and 2 to infinity to be equal to 0. Okay, good. Now, I just want to make one comment about analytic approach to such sums very quickly. So we go back to this idea of Selberg, who in 1950s looked at what he called as the generalized divisor function, which are the coefficients, Dirichlet coefficients in the expansion of zeta s to the power of z, but z is a complex number. And using the Perron integral method, he showed that this is x log x to the z minus 1 over gamma z. But the only difference is that since z is a complex number, the zeta s to the z has a branch point. So you can't just go around, it's not a pole, so you've got to do a last set. And when you do a last set, it turns out that you get the Hankel contour for the gamma function, and that's how you end up with the gamma z at the bottom. So this is Selberg's result, and it's uniform in any bounded circle, absolute z less than or equal to r. Now, Selberg noticed that you can deal not just with zeta s to the power of z, you can multiply it with some other Dirichlet series, which is convergent or analytic and real part s greater than half, and he gave some important examples of this to solve a certain question of Hardy on the local distribution of the number of prime factors. Okay. Now, the case of interest for us here is summation mu of n z to the omega of m. Now, why is this of interest? Because when I differentiate this with respect to z, the omega n comes down, and then I get z to the omega n minus 1. So then if I put z equal to 1, that's my sum mu of n omega n. So it can be obtained from the Selberg thing by differentiation with respect to z. So what you do is you write down the Dirichlet generating function, which is this, and you rewrite it in terms of the Riemann zeta function to the power minus z, and then you get this function, which is analytic and real part s bigger than half. And so the Selberg method yields this estimate here. Now what I'm going to do is the following. I can heuristically take the derivative of this with respect to z and put z equal to 1. That's what your summation mu and omega n is. So waving the hands, ignoring the error term, if I just do the main term and take the derivative, I end up getting x over log squared x. But that's only a heuristic. You still have to justify that, because you can't just take derivative like that when there is an error term. So Delange extended the Selberg's method by saying, instead of just having zeta s to the power z, you can multiply it with log zeta s to a positive integral power, a negative integral power. The branch point thing is still the same, so the Selberg method will go through. So now this is called the Selberg-Delange method, and this is a natural extension of Selberg's method, and Tenenbaum has a thorough account in his book about this. So when you do that, you actually end up getting, this is what you get heuristically, but you can establish this rigorously by the Selberg-Delange method. Okay, so now these are the details of the heuristic derivation by taking formal derivatives. But now what is happening is, and this Tenenbaum wrote in a letter to me after I pointed out these results, he says that you can actually get a series expansion like you get for the logarithmic integral of x. Here you can get a series expansion in terms of log squared, log cubed, etc., with an error term that's comparable to the prime number theorem. So he said you can prove the results that I have in a stronger form if you use the analytic approach. But the point I want to make is, when I use duality and go on to primes and arithmetic progressions, these analytic techniques we don't know how to apply, and even Tenenbaum didn't know how to apply. So the elementary methods that I had used previously with access theorem and so on, that still works. So one must have a great respect for elementary methods because they are of wide applicability, wider applicability sometimes than analytic methods, because analytic methods demand that your generating functions must have specific properties, because otherwise you cannot apply the analytic methods. Okay, all right, so moving on. All right, so as I said, the fundamental counting function for us is this well-known function psi of xy. So here I have it correctly, largest prime factor less than or equal to y. For a uniform bound, one can use something like this. But if one needs sharper bounds, you can use the Dickmann function, which is given by an integral differential equation or a difference differential equation. And this function actually decays quite rapidly, much more rapidly than the reciprocal of the gamma function. Okay. Now, if we're simple, but a point to be immediately resolved. The largest prime factor is uniquely defined. But there are two definitions for the second largest prime factor. You can either say, I take an integer n, I remove the largest prime factor, and I ask what is the largest one remaining. If the largest prime factor repeats, then it is the same prime factor remaining. Or you can say, it is the second largest prime factor defined to be strictly less than the largest prime factor. So one of the first results we have to prove is that there is little difference in these two methods of defining the second largest prime factor. That's what this theorem says. This theorem says that the number of positive integers up to x for which the largest prime factor repeats is this small. So you don't have to worry about which of the two definitions you use. In this paper, we use the definition that the second largest prime factor is strictly less than the largest prime factor. Okay. So this is the proof here using the psi xy, but I'm skipping it. Okay. The next thing I need to prove is that the second largest prime factor is almost always large. So what do I mean by that? By that I mean the number of integers up to x for which the second largest prime factor is not that big, so in this case I put an e to the root log n, is actually quite small. And here is a stronger version of that result. Okay, the reason I need this is we're going to use the prime number theorem and the prime number theorem for arithmetic progressions. So we're going to replace sums over primes with Stieltjes integrals, but when we do that, unless the p is large, it makes no sense. You don't use the prime number theorem for p less than 100. You only use it p going to infinity. So that's why I need a result of this type. Okay. So anyway, we've got this bound. It's technically difficult to prove. I've got some calculations here, but again, I will skip this. But an elementary proof can be given of that. Now, this result is the one that sets up everything. So this says that the number of integers up to x for which the second largest prime factor is congruent to L mod k is x over phi of k plus an error term of this type. Now, in my 1977 paper, when I proved the same result for the largest prime factor, this error term was x over e to the log x to the 1/3. I used the de la Vallée-Poussin error of e to the square root log x, but when I apply that, I pay a price because of the repetition. and that repetition gives me e to the log x to the 1/3. Okay, so there is a price to be paid. All right, so it doesn't matter. It's still much bigger than any high power of log x. So here I'm not able to get an error term of that precision, but this is what we're able to prove. Now, how do I prove this? I'm going to just explain a trick, and after that I will conclude by telling you about recent work. The trick is the following. You look at all the integers up to x and classify those integers according to the second largest prime factor. But when you do that, you have to ignore the primes because they don't have a second largest prime factor. So there is a built-in error of x over log x in your calculation due to you have to discard the primes. So that's what I have here. Okay. So the identity is your S2 of xp is the number of integers up to x with a fixed second largest prime factor equal to p. And when you do that, when I sum over all p less than or equal to square root of x, I get all the integers up to x minus the integers which have one prime factor, and those are the x over log x plus this. Now the next thing we do is I want to understand this. So I take the same sum, break it up, but I want to focus on the largest prime factor, so I write it in a certain form. But the main point is I express it in terms of this Dieckmann-de Broglie function psi. But the inner sum is now over the second largest prime factor p. Now, at this stage, so when you do the same thing for the second largest prime factor being L mod k, you have to have the same condition, but the p will now be L mod k. So that's what is going to be inside. But you see, I'm proving here that the second largest prime factor is uniformly distributed mod k, but in the inner sum, in my own opinion, I'm choosing roughly 1 over phi of k of the total sum, but I have to actually prove that the actual contribution is 1 over phi of k. So how do you do that with a sum? So here is the trick. You take the sum and you compare it with an integral from using the prime number theorem, and you study the resulting error. The resulting error turns out to be quite small, so you conclude that the term which has got the integral, which is written in 71 here, is actually x that you had originally plus the error terms that come from taking the difference between the sum and the integral. The moment you have that, you have a handle on the proof. Why? Because now when you go to the same sum with L mod k, which is what I call here, what you now do is you compare it once again with the integral, but now the integral is using the prime number theorem for arithmetic progressions. Now in an integral, it makes no sense to say you take 1 over phi of k of the points on the interval from 0 to 10. Of course, in measure theory, yeah, measure 1, 10 over phi of k. But here, it means you put the constant phi of k outside of the integral. Therefore, when you convert this into an integral, automatically the 1 over phi of k comes outside. And therefore, you are able to show that the original sum is x over phi of k plus this, and therefore you prove that the sequence of second largest prime factors is uniformly distributed modulo k. So it comes really out of this trick. This trick was there in my 77 paper, but to use it here for the second largest required more difficult calculations. And it's the same trick that this younger group is using when they are using the Shevchenko density theorem. Okay, so once you have that, I go through the same thing that I had before to show that this sum is little o of x. Then I show that the sum with the largest prime factor with the so I show using Axel's theorem, and finally when I use the uniform distribution result, that's the x over phi of k. You see there 1 over phi of k comes out, this sum becomes small, so you end up showing the smallness of this expression. Axel's theorem method works in exactly the same way, but I want to just show you a miracle takes place when you go and do the integral part. When you do the integral part, what happens is you do the integral part with this difference. That's what is there in the duality. But what I want is mu n omega n of f of p of n. So I got to bring this minus 1 to the other side and make it a plus 1. But when I do that, that also is an x over phi of k coming to the other side. So these two things cancel, and you end up showing that this sum with the omega is actually little o of x. So the entire procedure goes through and we get our main result. So the miracle is really the cancellation. So now let me point out something else. So there are 2 or 3 things that come out of this. see, I started by showing this result here. In a similar vein, I can now show that if I look at omega n like this, I get little o of x. If I use fractional part, I get little o of x. Hold on. When I get integral part, I get this. And now you will say, this is the same theme. What's the big deal? What is the difference? The difference is right here. When I do this, I end up getting a function of the second largest prime factor. But if I only look at the -1, I get a function of the largest prime factor. So I end up getting this difference. So what this means is, when my f is the characteristic function of primes in an arithmetic progression, the average is still the same, 1 over phi of k. The two things cancel. So now my theorem will be reformulated as follows. If a function, bounded function on the primes has asymptotics, which is kappa, and if the average on the second largest is kappa, the same kappa, then this sum becomes 0. Now, why do I emphasize this? I have a problem in my paper. Does there exist a bounded function on the primes such as maybe it has one average on the largest prime factor and another average on the second largest prime factor? I have not been able to find such an example. I conjecture that such a function does not exist, but I don't have a proof that such a function does not exist. But for my purposes, for my function, which is the characteristic function on primes in arithmetic progression, all thing is over. So in conclusion, let me say that my student, Seon Sangupta, has taken these same results and now applied it in the context of algebraic number theory and obtained similar slicing results from mu and omega n using the Shabatarov density theorem. And the general result that I have, I'm working with another PhD student of mine, Yazan Alamodi. So this has been done in the context of Galois extensions and actually more general extensions by Ken Ono and his group. I give you a whole bunch of references for you besides my paper, and these are all papers of the Ono group, but we rely heavily on the Lagarius-Odlyzko strong form of the Shabatarov density theorem. But I think this paper will have as much implication and excitement as my 1977 paper, except that for 40 years, nobody looked at these higher order dualities, and I thought I should present this at this conference. Thank you.
So thank you very much. You succeeded to show your 72 pages in half an hour, what you did in 1 hour before. And also now we know much more about the second prime divisor of the numbers. And I expect next time you will tell us about the third prime divisor.
Okay. Being worked out with Sengupta again.
Okay. So are there further questions?
Can you say a few words about what is known for non-Galois extensions like this? You said Ono was doing something.
So whatever is known is for Galois extensions. I don't think there is any paper that we have seen so far for non-Galois extensions, but now let me make one point here. Madeline Locus Darcy, the PhD student of, former PhD student of Ken Ono, first did it for Galois extensions of Q. And of course used the Shabatarov density theorem in that case, noting that when the extension is a cyclotomic extension, that is abelian, and therefore the conjugacy classes all have size 1, so this ratio is always 1 over phi of k. That corresponds to my case, which is the prime number theorem for arithmetic progressions. Then subsequently, Sweeting and Wu considered any general Galois extension of an arithmetic of a number field, not necessarily of Q. But when they did that, they had to formulate the Mobius function and my duality identities in terms of prime ideals and therefore and their norms, and then the smallest and largest and so on. So they had to establish a bunch of results before they could do that in that setting. But for the regular Galois extension over Q, the initial results that were obtained did not require such a complicated thing. Okay, so it went through routinely. So it's yours a good question, but I don't know of any results. But I think this opens up several possible avenues of exploration.
Any further question? No? So let us thank the speaker again.